Hello and welcome to Let's Code Physics. I am really excited to get started today with a new series about self-driving cars. Self-driving cars have been an interest of mine for a while because I do not like driving. I will be honest with you. I feel like I could spend that time doing so many better things for me, and that if a computer were in control of my car, it would do a much better job. And so I am eagerly awaiting the day that I get to buy a self-driving car, and even more eagerly awaiting the day that all cars are replaced by self-driving cars. As we're developing self-driving cars, there's basically two functions that need to be implemented in a self-driving car. One is strictly navigating the road. So let's suppose you've got a road that goes like this, and maybe even, curves back around on itself or something. You need your car, I'm going to be drawing cars in red, you need the car to be able to navigate that road. So let's just say this is a single lane, even with no other cars to worry about. The self-driving car has to know that here it needs to go forward, here it needs to start executing a turn, then it starts needing to turn the other way, then it needs to keep turning in that direction, then it needs to turn the other way, and then it needs to make a U-turn going this way. And it needs to not get confused along the way in terms of, recognizing where the road boundaries are and how to best proceed along that path. This has been pretty straightforward to demonstrate to people is attainable with our current technology. When people take test drives, test rides of self-driving cars, studies have shown that people can get pretty accustomed to having the car, navigate these turns, and even navigating obstacles on the road. Like say there's a chicken, trying to cross the road over this way. The car's navigation system can adjust for that by braking or by swerving around the chicken, doing whatever it needs to do. I think probably braking is a better option there, but you can brake and swerve away from the chicken's direction of travel. I'm assuming here that the chicken is crossing the road, and I will not ask any questions about that. But the other thing that self-driving cars need to be able to do is to be able to navigate intersections. So let's say you've got an intersection with, say, a couple lanes this way and a couple lanes going this way. Right, so say it's a four-way intersection. So you'll have, a car that's coming in from this direction, a car coming in from this direction, a car coming in, and let's say this car needs to make a left-hand turn, and let's say this car needs to make a right-hand turn. Self-driving cars, one of the beautiful things about them is that they can communicate with each other. Or rather with the intersection. So say you've got a computer set up at the intersection that can dictate to each car when they are supposed to go through the intersection. So rather than having to have human drivers trying to remember what the rules for stop signs are, and many people out there don't know the rules for stop signs. I discover this every weekend that I go to the town center. But what can happen is that the machine, the computer at the intersection can assign when these cars can go through. So the intersection can manage its own traffic. And if you time it just right, you can make it to where these cars don't ever actually have to stop. They just adjust their speed slightly so that they miss each other as they're going through the intersection. And it's this beautifully choreographed movement across this shared common space. And so while this piece, the road navigation, is pretty easy to demonstrate to people, this intersection management is not quite think Google is yet putting a whole bunch of people into a whole bunch of self-driving cars and putting them on test tracks with intersections, although that may be coming soon. Either way, that's not as accessible, and it's difficult to see that management from just the perspective of a single car. What we need is a bird's eye view. Maybe this bird, well, I guess a chicken can't get a bird's eye view, can it, if they don't really fly? So a non-chicken bird's eye view, a flying bird's eye view, a top-down view, that's what I'm looking for. So what we need is a top-down view of this intersection management, and that's the part that I would like to focus on, is seeing how we can get self-driving cars draft at intersections. Before I go any farther, I should cite my sources on this. A lot of the work that I've been reading about with self-driving cars is coming from this paper right here, which I will link to in the description below. It's a group from primarily Carnegie Mellon, it looks like, and then a few folks from General Motors, Caterpillar, Continental, Intel. So I'm guessing these are the folks who mostly backed the research, and these are the folks who primarily conducted the research. That's usually the way the groupings go, like that. Oh, who knows? I could be wrong about that. And so what I've done is I've started a basic self-driving car simulator. I don't have any intersections yet, right? So that's the goal of this study, is to build up toward intersection management. But I first need to get that first piece where my self-driving cars can navigate the road in front of them. So let's actually expand this view here. So what I've got set up so far is a self-driving car. So the car is going to be red, and as with black hole battles, the graphics will get better as we go along. I've got my self-driving car here in red. I've got my road here in gray. It's made of these pieces, which we'll look at in just a second. And then I've got some buildings up here. Those are just for reference. Those aren't actually doing anything right now. Eventually we'll have a city populated with buildings, you know, in these, along these roadways, and at the corners of the intersection, etc. So what I first wanted to do was run this thing and then show you how it's working. So my first goal has been to get this red car to follow the lane that it's in. So let's run the code and see how she goes. Okay, cool. So you saw a yellow line there. That's basically the center line of the lane. I'm not sure why, but it's moving underneath the lane right now. I've set up some view controls so I can move the view within the game to see how things are going, and I can also click on an individual car and follow that car here in the game view. So this is the view you would see if you compiled and ran this code. So you can see the car is navigating along the road. It is identifying when it needs to turn, so it's rotating and it's adjusting its velocity. Never mind those yellow lines for right now. We'll talk about those in a second. So the car is successfully navigating a variety of turns. I've had this thing kind of loop back around in the same direction, and it makes it all the way to the end. Now, this is the end of the road, so here the car would be parking, so we're getting an error here because it doesn't have any more points to consider, and it's just sailing off into nowhere, so we're not worried about the end of the road just yet. I'll add in something for that later. So I'm pretty proud of this. I think it looks neat, or it's functioning neat. I guess it looks kind of basic. So let's take a look, shall we say, under the hood and get an idea of how this thing is working. So the first thing we've got, let's take a look at our lane here. You notice that the lane object is made up of several different pieces. It's made of lane squares and lane turns. The lane squares are these basic pieces here. So that's the piece you would use to make a straight going lane. The lane turn is a further collection of very small pieces. So each one of these quads within here represents one slice within the lane turn. And this just represents having the road curve by 90 degrees. If you wanted it to curve by less than 90 degrees, you could just take the last few of these quads. Say you only wanted it to turn 45 degrees, you could take half the quads and delete them, and then this thing would rotate by, would turn the car by 45 degrees. You'd have to turn your lane square by 45 degrees to keep it going that way, but it's pretty straightforward to do. So this whole collection goes into this lane. Each one of these pieces has a collider on it. Each one has a box collider so that we can tell where the car is in relationship to this lane. So this car is over a piece in this lane, so that tells this car you are in this lane. We'll take a look at how that works in just a second. But overall, this lane has a script associated with it. Line. That's a term used in the paper I was referencing earlier, so that is standard terminology for self-driving cars. What we have to do to find the lane's center line, this is the curve that goes along the center of the lane. What we do is we look over. We only have to do this once in the start here because the lane itself is not going to change from one frame to another, so that's nice. And basically what we do is we look at each piece within the lane. So, oh, and I forgot to up my font for you. There we go. What we do is we look at each piece within the lane. So within a lane, I've got lane turns and lane squares. So it's going over all of those pieces there. And it's first checking whether that piece has any pieces of its own, has any children within it. So for example, a lane square doesn't have any pieces within it. It's sort of at the bottom of the ladder. Lane turn, on the other hand, has all of these quads within it. So these are the children within lane turn here. And so for so basically this is for the lane turns, this is for the lane squares. I don't have any other pieces yet, but you can imagine if I had something more complicated, I'd have to add in another chunk here. And so basically what we do is we're adding to this list of my center line the position of each gray piece, of each quad. So for each little rectangle within the lane turn, or for each square that is a lane square, we're adding its position to the list my center line. So my center line is going to be a list of vector 3 positions of where each of these lane pieces is. Of course, that's not necessarily useful if I added this one in the list first, and then this one, and then this one, and then this one, and then this one. So it does. So the next thing the code does is performs a sort of this list based on how far away they are from a starting square. So I just designate one piece as a starting square. So in this case, that's the leftmost square, and it sorts the pieces based on their distance from the starting square. Now that's not entirely perfect of a sort, because, for example, this piece in here, the pieces within this lane turn here are closer to the starting square than the lane pieces are up in this curve, because it's closer in terms of the z direction here, while being just as close in the x direction. So it thinks that these need to come next compared to these. So we're going to fix that when we come to the cars routine. But this just sort of performs an initial sort to get the most. The next piece we need to look at is the car itself. So if I click on the car over here, I've got a few codes in here. One is just click to follow. This is just the script that allows me to click on the car during the game and have the camera follow the script. So not a huge problem there. Another one I need is this code, which lane. That stores the information of which lane the car is in. So right now I've only got this one lane, so this whole long gray thing is a single lane, but in a second I'll be adding a second lane, this one called loop over here. And so it needs to keep track of which lane it's in. So the way it does that is it just looks for a trigger enter. I need to delete this stuff up here. It doesn't need a start or an update. There we go. Not that the comments really contribute to the running of the code, but it's just cleaner. So basically I have the lanes set up to be triggers. So rather than performing an actual collision where the car collides against the lane, it gives me a flag in this subroutine whenever the car enters the lane. And so it's checking for whether it's had the trigger with the lane here, and then it's setting that lane as my lane, so that lane itself. So in other words, this red car here, because it's over the collider for this lane square, it knows that it's in this lane here associated with this lane square. It goes up from the lane square to lane by using this .root.game object. So .root says take me all the way to the top to the very utmost parent object, and then game object is saying, all right, now reference the instance of that game object. Which is pretty cool. So the car knows which lane it is in. That's important because the car needs to know which center line to follow. So here we've got the primary code that's driving our car, is this generate trajectory code. It's got a bunch of stuff here at the beginning that we'll go over as we need it. Let's see, the first thing we need to do is we need to get the car's collider so we have an idea of how wide the car is to make sure the car doesn't leave its lane, and then we need to get the car's rigid body to determine the car's velocity. Okay, here in the update, this is where all the fun stuff happens. So I've got everything split up into modules here. The first thing we do is determine which direction the car is traveling. That's just using the rotation of the car based on how it's rotated in the y direction. We've got the y-axis coming up out of the screen, so all of our car orientations are going to be given in terms of the y rotation. And so we're just creating a unit vector to give us this direction. That'll be important in a second because we need to know what direction the car is traveling so we know which piece of the lane is in front of the car and which piece of the lane is behind the car. Then we need to retrieve which lane this car is in. So this is just storing that information in WL for which lane. We also need to store the information about the lane's center line, so we're storing that in FMCL for find my center line. And then the first piece we do here is we determine a motion goal. So this is going to be the point that the system is trying to reach. Right now, this is simply the end of the lane. So right now, our only goal is to get to the farthest piece of the current lane that's in front of the car. So here what we do is we look throughout the pieces within the lane, evaluate which ones are in front of the lane, and whichever one of those is farthest away is our goal piece. We'll expand this in a future video because there are other goals to consider on the road, for example. So you might want to avoid a collision with another car. You might need to swerve around a chicken crossing the road. You might need to stop for a barricade in the road. Right now, though, our goal is simply continue along in the lane, so there's not much there to talk about now. The next thing we do is we retrieve the center line. So we're going to generate the center line. Now this is a little bit different than the lane's center line in that we're only concerned about the points that are in front of the car. So what we do is we take the my center line list from FMCL. So this is the lane's center line. This is the basically, if you imagine, this is the line down the middle. Well, not the line down the middle of the road because those go in between lanes. But this is I know. If you imagine that line of oil streak that you get in the middle of the lane because of the cars dripping their oil. This is what that line is. Finally, I got a metaphor for this thing. Actually, I wonder if any self-driving cars use that to help them navigate. That would be interesting. So what we're looking for here is we're looking for the relative position vector going from the point that we're looking at in the center line back to the car's position. And basically, we're checking for whether that point is ahead of the car. We're doing that using the dot product. So the dot product looks at the angle between two vectors. And if your dot product is positive, then that piece is in front of the car, meaning it's mostly in the same direction that the car is pointing. If not, then meaning if it's negative, then the piece must be behind the car and we're not going to worry about it. So we're only adding to our car's center line trajectory the points in the lane's center line that are in front of it. That way the car doesn't get confused about trying to go to points that are behind it. And then here we're doing another sort. So this is a shorter list. These are only the points in the car that we're concerned about. And it's being sorted now by the distance between the cars. So it's much like the sort we had before, only now instead of being sorted by distance from the starting piece, it's sorted by the distance from the car's current position. So the only thing to do after that is to move the car. So we've figured out the center line that the car needs to follow. Our next thing that we need to do is move the car. So all the way down here, we've got a subroutine to move the car. This involves two things. It involves both adjusting the car's velocity vector and rotating the car. So the first thing that we need to do, actually I figured out that this piece was wrong, so let's take that out. The first thing that we need to do is we need to figure out in what direction we're wanting to move the car. And basically we need to move the car from its current position to the beginning of the center line that it's trying to follow. Remember, it's not considering any points along the lane center line that are behind it. The only things on this list are the points in front of it, and the center line of 0 is going to be the closest because of this wonderful sort that we did up above. And so what we do here is we're just defining a move vector. Again, this is a unit vector because we're normalizing it. So this is just giving us the direction the car needs to go in. And so we're setting the car's velocity to be in the direction of the move vector with a magnitude of the speed. Right now, we're just doing the speed limit along the road. I set that to be 1. If the car is behind another car, this could be the speed of the car in front of it so that it is keeping traffic moving along. If we need to come to a stop, we would change this to 0 so that the car comes to a stop by the end. But again, that's going to involve more complicated trajectory planning, so we will worry about that in a future video. Right now, we just need to get the car to follow along the lane. And then, of course, it looks a little creepy if the car is just moving and not rotating, and also we need to keep track of what direction it's moving in. So here we are rotating the car. We are rotating it about its own position, so we're rotating it about its center, about the y-axis, and we need it to rotate in the direction of the move vector. So we need it to rotate in the direction that it is moving. And of course, we're subtracting off its current orientation, so that way, if it's traveling at an angle of 45 degrees, it doesn't need to, and it needs to be traveling at an angle of 45 degrees, it doesn't need to rotate anywhere, so we're taking the difference between those two. Okay, and that's pretty much it. The only additional piece we have is that centerline trajectory being plotted, which is being created by using a Bezier curve. I showed you the setup for this in a Black Hole Battles video, so this is the same code as the look ahead back in Black Hole Battles, so I'll link to that in the description below. And so what we get is a pretty nice smooth sailing car. You can see the trajectory better here. So for example, you see how well, you saw it a second ago, the center line was jiggling back and forth here. That's because of that issue with this being plotted from the starting square here, from the car, but we're not really worried about that because the car isn't at those points yet. Or right now, it's ignoring these squares because technically these pieces are behind the car because the car is pointing this way. These are behind it, so it's ignoring those. But the car, it's not yet planning its movement over this way. It's only planning it one frame to the next. And so once it gets, I guess let's move the scene over to here. There we go. And so once the car gets around to this point, why does my scene look different between those? I'm not sure. Once the car gets around this curve here, now suddenly these points are in front of the car. And of course, it's having the same issue over here. It's going back and forth between these. But again, that's going to fix itself by the time the car gets around another couple of corners. Again, we get these jumping back and forth, but again, that's happening at the end point. It's not messing up the car's next move. The same type of correction happening up here. And so we've got the car following the lane as it's supposed to very nicely. Okay, so one thing with this, and that I'm pretty happy with, because I know it's going to work. I've added in another car. I currently have it deactivated, so let's add in another car, and this will be the last thing we do because our video is coming up on about 25 minutes here. And I've created a second lane. This one, however, is a loop. So you notice this one goes around back on itself. And my question to myself was, all right, if the lane goes back around on itself and forms a loop, is that going to be a problem for the car? So we'll leave this other car in because it's fun to see that they both operate independently. But what we're going to do now is we're going to focus on the motion of this car down here. So the two cars are functioning independently just fine. So this car moves along here, so it's only considering the parts of the path that are in front of it. So our trajectory is going forward. I need to adjust the y value on the trajectory so that it points upward. Actually, let's do that in a second. So the car manages to come around, and you notice it's got points going ahead of it. That's because it gets the entire group of centerline points, and it only considers those that are in front of it. So as it moves around, the subset that is in front of it changes. Oh, my other car reached the end of the road. This one's going along nice and fine. Let's make a really quick adjustment to this car's center line. I need to move its Y value, its Y position up a little bit. Let's try that. See if that makes it more visible. Lo and behold, it does. Hooray. Okay, so I'll make that adjustment on this one as well. And so you see, it's getting that same, end bifurcation over there, but we're not really worried about that because that's not where the car is headed right now. So I'm pretty excited about this. I've got cars that can follow along the lane. The next thing that I need to work on is how these cars adjust with things like changing lanes or making turns. Because right now, we're assuming that they're in the center of the lane and they're staying in the center of the lane. If this were an intersection and the car wanted to turn left, how would it plot that? Trajectory. What happened there? That's not supposed to happen. Okay, apparently I have some other things to look at because this car just went the wrong way around. So I need to take another look at how that is working. I hadn't run this for that long, so thank you all for being here and just in time to see my mistake there. I think I'll keep watching this to see if and when it bounces back around. So next time we'll talk about how we're going to solve that. So thank you so much for watching. I'm looking forward to this series. I will see you next time. Bye-bye.